On this episode of Electronics Tinker, I will be showing you Protor, my new 65 CO2 based computer.
So here we are in PuTTY. Right now I'm running at 115,200 baud over the serial port. So if I go ahead and reset the computer, it'll bring up a prompt character, and typing in a question mark will display the help menu. So there's 5 commands available: to display the help menu, toggle the interrupt enable bit, run a program from a specified memory location, store data into memory, and then read data from memory. The system is based on the Apple One's Woz Monitor, except I've added a few extra commands such as the help menu and the toggle bit, or the interrupt to toggle. And I've also expanded the input buffer from 127 characters to 255 characters. So the first command besides the help menu is the toggle interrupts command. So if I type in a T, that will display whether or not the interrupts are enabled or disabled, as well as flip that bit in the status register. So by default, when the system boots up, the IRQ interrupts are disabled, but by typing that T, I just enabled them. And the other thing is the commands are non-case sensitive, so I can use either an uppercase T or a lowercase t. And every time I type that character, it will flip that bit back and forth. The other thing is, once the computer is done executing one command, it goes back to the input buffer and continues parsing until it gets the end of line character. So that means I can use multiple commands in one line and execute them all at the same time, or at least sequentially. So that means if I wanted, I could flip the interrupt enable bit back and forth 255 times, although that would not be very useful. The next command on the list is the store command. I'm going to skip over the run command, at least for now. So the lowest 8K of the system is RAM, which means from address 0000 through 1FFF is all RAM. And the system only uses from the 0 page and page 1 and page 2 of the memory. So that means that past 2FF hex, the rest of the system is free, at least RAM-wise. So that means that at address 300, that's RAM that's not being used. So I can store in a small hello world program, originally written for the Apple One computer, which I've now changed slightly just so that it works with my output routines on the computer. So that part that I've just typed in is the actual code for the Hello World program. So it basically just loads the X register with the number of bytes to be sent. It then loads the accumulator with the base address of the text that's going to be sent, and then the base is indexed from the X register. So that means it starts at the end of the index and works its way down. It then puts the character that it just got out to the display, and then it gets the next character, and it continues on until the X register is 0, at which point it will jump to the reset vector and just reset the computer. And then after that is the actual text that is being stored. So this is all in ASCII. So there it is, and if I wanted to check to make sure that what I typed in is actually correct, I can use the view command. So there it is, and I can go through and check it, and as far as I can tell, that looks correct. So I can run that by typing in the base address of the program and typing in an R, and again, the commands are non-case sensitive, so I can use either an uppercase or a lowercase, and then just hit enter to run. And there we are, hello world. So whenever a program is run, it will display the actual address that the command is, or that the base of it is. So right now at the address 300, we stored the value 82, and that's why it's showing that at 300 there's the value 82. After that, it runs the program, which displays hello world, and then that's it. So during some of the initial testing of the ACIA, I was having problems displaying or getting it to work correctly. So I wrote a small routine that I could use for checking to make sure that all of my settings were correct on it. And I just stored that right at the base of my EEPROM. So all it does is it pulls the status register of the ACIA and waits until it receives a byte. And then once it has, it loads that into the accumulator, compares it with the value for an escape character. And if it's not, it will send that back to the display. But if it is an escape character, then it will return back to the monitor. So I can run that. And then whatever I type just gets echoed back to the monitor. And it'll just go on forever like that until I hit escape, at which point it returns back. I've also written a debugger test program. So whenever the computer encounters a break instruction, it jumps to the IOQ interrupt vector, and I check to see is it a hardware interrupt or a software interrupt. If it's a hardware interrupt, I just jump to an indirect jump from the address 0302 hex. But if it's a software interrupt, I will jump into the debugger program, which will display the values of all the registers of the CPU. So that's stored at E100 and E10A. So the actual program, just for testing it, is quite simple. So it has a break instruction followed by a buffer byte. So the processor views the break instruction as two separate bytes, even though it's only a 1-byte instruction. So I have the 42 in there just as filler for my assembler. Then the 6901 is load the accumulator, or add to the accumulator 1. CA is decrement the X register, and C8 is increment the Y register. The EA is a no operation, so it just basically skips that byte. The 48 is they push A onto the stack, so that way I can decrement the stack pointer. And then the 4C00E1 is jump back to the beginning of that loop. So if I run that program, the computer will show me I've had a break at that address, and I can press any key to return back to there. So basically what that means is I can put break instructions periodically throughout my code, and it will jump to this and display the value. That way I can see what's going on at every single step in my code if I wanted. So if I press any key like the spacebar, it'll continue on just jumping back to where it was. So it displays the program counter, the accumulator, the X register, the Y register, the status register, and the stack pointer. So each time I press that, you can see that the program counter is the same because the break address is always at the same location. The accumulator is incrementing because I'm adding 1 to it each time. The X register is decrementing, and the Y register is also incrementing. And then also the stack pointer is decrementing because each time I'm pushing the accumulator back onto the stack. If I hold this down, let's see, you can see some of the bits change in the status register. Almost there. There. So the third line up from the bottom is where it started changing. You can see one of the flags in the status register changed, the negative flag, because the Y register was the last one to be changed before the break instruction. So since the Y register flipped over to 80, it's now saying that it's negative, and you can see that in the status register. To get out of the debugger and just return back to the monitor, I can press escape, and here we are again. The final program to show you is the audio output program. So all this does is it takes the any input bytes it gets and sends them straight to the audio output register. So it pulls the ACIA for new data, and as soon as it gets a new byte, it will load the accumulator with it and then store that at address 2000 hex, which is where the octal latch is located. And then after that, it has a branch always instruction back to E200. This is the 65C02 version of it. So because it's from WDC and it's the more modern CMOS version of the processor, I can use instructions like the branch always that will speed things up a little bit. So sometimes in here you'll see like a push X or things like that, and that's just because I'm running the newer version of the processor. So the code here is not 100% compatible with the original NMOS version of the processor. So anyway, I can run this command here, or run this program, and it won't actually do anything, at least visibly on the screen. And I can type all I want, hit escape, it won't get out of it. So I have to switch programs, and I'm going to go over to a program that'll send an audio file to the computer over the serial port. And what I've set it up as is I took an audio file and then I put it into Audacity and converted the bit rate. Instead of having 44,100 bytes per second, I changed it to 11,520 because I'm running a serial port. It has one start bit, one stop bit, and then 8 data bits, which makes 10 bits. So if I take the 115,200 baud and divide that by 10, I get the 11,520 bytes per second sample rate that I need. So I'm going to go ahead and switch over to that, and I'll put the headphones onto the mic so you can hear it. So here we are in the file send program. It's just a batch file I've written. So I can put in a file name, and it'll send it over the serial port at whatever settings I've set into the actual batch file itself. So if I hit enter, it will set up the COM port with 115,200 baud with no parity, 8 data bits, 1 stop bit, and then no handshaking. And then it starts sending the actual file over. So that's what it's doing right now. If I put the headphones onto the microphone, you'll be able to hear what the computer is doing. So it's just taking the byte and sending it straight to the audio output register. So I've resampled the actual file so that it's only 8 bits instead of 16 bits like the original one. And then the other thing is, originally I had this testing at 19,200 baud, and that meant that I only had a sample rate of 1,920 bits per second, which was kind of a problem because the audio was barely recognizable. You could tell there was a little bit of music there, but it was not like very good at all. So I changed the schematic around a little bit so that I could have a higher bit rate. So right now running at 115,200 baud, that means I can have 11,520 samples per second, which is way better than 1,920 that I was getting before. The output of the audio circuit has the 1 kilo ohm resistor and the 0.1 microfarad capacitor as a sort of filter on it. So that cuts off frequencies above about 1.5 kilohertz approximately. And that means that a lot of the high-pitched squealing that was in here is gone now. Originally there was quite a bit and it was not very good sounding, but I added that in and it did get rid of quite a bit of it. There's still a little bit of static and extra noise in the signal, but it's not bad compared to the original value. So the program will just continue running until it hits the end of the audio file, at which point it'll just close the batch file, and that'll be it.
So the reset switch does exactly as you would expect. It resets the processor when you hold it down. The pause switch is tied straight into the ready pin on the processor. So the pin on the processor is tied straight to power through a 4.7K resistor. And then when this switch is flipped, that pulls it down to ground, which tells it, hey, stop in whatever it's doing, and then it'll just stay there until I release the switch. Right now the computer's running at 1 megahertz, but initially I was running at around 5 hertz. So having this on there in that initial testing was really useful because that meant that I could just pause the processor whenever I wanted, take a look at the lights and check, make sure, okay, is this in the right location and is it executing the code correctly? The volume knob is just a standard 10K potentiometer, which is hooked straight in line with the audio output to the 3.5mm headphone jack. So coming around to the back side, things get a little bit messier, but I did try to color code some stuff. So all the yellow wires are the data bus along with this bundle of orange wires. The black and blue wires are the address bus for the most part. And chip-wise, up here in the left-hand corner is the 65C51 ACIA along with its timing crystal. The 65CO2 is here in the middle, along with a 1 megahertz oscillator. There's an octal latch for the audio circuitry, and an 8-bit resistor DAC for generating the analog waveforms. The operating system is stored in an 8K EEPROM, and for scratch RAM there's an 8K static RAM. All of the chips are decoded using a 74HC138 decoding chip, and the RS-232 interface is provided by the MAX232 chip that will interface between the logic levels of this and the RS-232 levels needed for my USB to 232 adapter.
Here's the schematic. On the left-hand side you can see the 65CO2, and going over to the right is the 8K RAM, the 8K EEPROM, the 65C51 ACIA, and the MAX232 chip. Down toward the bottom is the 74HC138 decoder IC, the reset and ready switches, and the 74LS374 octal latch along with the resistor DAC and the audio output filter. So on the 6502, I have tied the IOQ NMI bus enable and set overflow pins to VCC through the 4.7K resistors. That way they don't trigger any miscellaneous interrupts from them floating, and also to enable the buses on the processor and to prevent the overflow flag from spontaneously flipping. On the RAM, I've attached all the data bus wires from the processor straight into the data wires on the RAM, but I'm only using address pins A0 through A12 from the processor for the RAM. And that's because the RAM is only 8K and that's all I need. And same goes for the 8K EEPROM. Also on the RAM is the read-write pin, and that's tied straight to the read-write output on the processor. But on the EEPROM, the read-write pin is tied to VCC through a 4.7K resistor, and this is so that I can prevent any accidental writing to the EEPROM when the computer boots up or there's power fluctuations. Connecting to the ACIA is the read-write pin, the phase 2 clock, and the reset lines, and these are all just as control signals between the processor and the ACIA. Also, the data bus is connected, and the lowest two address lines, so A0 and A1, are connected to the register select pins. The pins 16 and pin 9 on the ACIA are also connected to ground through 470 ohm resistors, and this is to enable the transmitter, because if these are not connected to a low potential, then the transmitter will be disabled and I can't use the ACIA. Also, the pin 2, which is the high chip select, is pulled to VCC. That way that one is always active. And then the other chip select, pin 3, is the negative going chip select. So that's going to pin 8 on the 74HC138. And that's the enable pin from the address decoding. On the ACIA, I have connected the
normal resonant circuit that's used. So between pins 6 and 7, there's a 1 megohm resistor and a 1.4 or 1.8432 megahertz crystal with a 33 picofarad capacitor on those pins. But using that setup, you can only achieve a baud rate of 19,200 baud. So I added a jumper between pins 7 and 5 so that the 1.8432 megahertz signal can go straight into the receiver clock. And then in the code, if you set the baud rate to x16 of the receiver clock, that means that it's only dividing that frequency by 16 instead of 96, which means that I can get the higher baud rate of 115,200 baud that I've been operating this on. Also on the ACIA is the pin 12 and pin 10, which are the receive data and transmit data, and those are just tied straight into the max 232, and then that translates those into the RS-232 levels that I need to communicate over the serial port to my computer. In the right hand corner is the 74LS374 octal latch, and I've just connected the D0 through D7 inputs straight to the data bus. And then the latch enable pin, which is pin 11, is connected straight to pin 12 on the address decoder. Upon a rising edge on that pin, whatever's on the data bus will be latched in and then output on the Q0 through Q7 outputs, which goes straight into the resistor DAC and creates an analog output, which goes straight through the 1 k ohm resistor and the 0.1 microfarad capacitor as a filter, and that goes out into the audio port. Moving over to the 74HC138 address decoder, the A13 through A15 address lines are connected into the decoding pins, so pins 1 through 3. These are the output select lines, and this divides the entire memory address space into 8 banks of 8 kilobytes each for the total of 64 kilobytes that the processor can access. Pins 4 and 5 are the inverted enable pins, so they have to stay low in order to enable the outputs on the chip, and they are tied to ground through a 470 ohm resistor. And then the outputs used are pin 15 for the RAM select, pin 7 for the ROM select, pin 9 for the ACIA select, and pin 14 for the octal latch select. The last pin on it is the pin 6, which is the positive enable pin, so it enables the outputs when this pin is high, and this is tied straight to the phase 2 clock line from the processor. Originally, I just had this pulled up to VCC through a 4.7K resistor, but I was having problems whenever I jumped to a subroutine and tried returning from it. The processor would always fetch the correct low byte of the return address, but the high byte was never correct, and this took quite a bit of debugging to actually figure out what was going on. Basically, when the processor has the JSR instruction or jump to subroutine, and it's pushing the high and low bytes onto the stack, there's nothing to disable the RAM between those 2 bytes because the read-write line stays low between both of them, and the address lines stay the same except for decrementing by 1, which means that there's nothing to tell the RAM to latch that data in. By adding this phase 2 line into the enable pin on the selector, the processor disables the RAM temporarily between both of those byte writes, which means that both the high byte and the low byte of the address are stored correctly, and that fixed the return from subroutine problem that I was having. Finally, in the middle of the bottom is the ready and reset switches. Both lines on the processor are pulled to VCC through 4.7K resistors, and the reset switch has a 0.1 microfarad capacitor on it to help with some debouncing on the circuit. That's all I have for this video. If you liked it, be sure to leave a like, comment, or maybe even subscribe. And on the screen now is my previous computer experiment, another computer using the 65CO2 processor.